Welcome to Lecture 15, 4.1, Scatter Diagrams and Correlation. So for our definition, the response variable is the variable whose value can be explained by the value of the explanatory variable, or the predictor variable. So for first example, it seems reasonable to think that the speed at which a golf club is swung increases, the distance the golf ball travels also increases. Therefore, we might use a club head speed to predict the distance. We call the distance the response, or the dependent variable, and the club head speed the explanatory, or predictor, or the independent variable. Most of the time in math, we use dependent and independent, but for statistics, we tend to use response and explanatory. Alright, so by definition, for Objective 1, draw and interpret scatter diagrams. So a scatter diagram is a graph that shows the relationship between two quantitative variables measured on the same individual. Each individual in the dataset is represented by a point in the scatter diagram. The explanatory variable is plotted on the horizontal axis. Generically the x values, and the response variable is plotted on the vertical axis, which is generically the y values. So let's take a look at our first example. A golf pro wants to investigate the relation between the club head speed of a golf club, measured in miles per hour, and the distance in yards that the ball will travel. He realizes other variables besides club head speed will determine the distance the ball will travel, such as club type, golfer, ball time, and weather conditions. To eliminate the variability due to these variables, the pro uses a single model of club and ball, one golfer, and a clear 70-degree day with no wind. The pro records the club head speed, measures the distance the ball travels, and collects the data in the table shown below. Draw and label a scatter diagram of the data. So whenever labeling data, or labeling your graph, I always take a look at the range of values we have. The highest number we have is 105. So, and the lowest number we actually have is 100. I'm going to stick between 100 and 105. So I'll start at, actually lowest number was 99. I'm incorrect. So let's go ahead and go with 99. And then we'll do 100, 101, 102, 103, 104, and 105. We're actually going to hit our graph a little bit here. Alright, and then let's see. So that was my x values and my y values. The distance the ball flies. Lowest value we see is 258. And the highest value we see is 277. So we're going to kind of stick in between there. So let's start at 255. And then we'll go in increments of 5. So 260, 265, 270, 275, and 280. Okay, and let's go ahead and label our chart. So we have club head speed, and for the other one, distance ball flies. As usual, in these videos, I'm showing you how to do all this work by hand, which is how I'll ask you to do it on the exams because I give you small data quantities. If you have large data quantities in the homework, feel free to use any of the StatCrunch or Excel. If you need help with any of that, please let me know. Normally they have little videos on how to use that as well. Okay, let's go ahead and plot the points. So the first point we have is 100, 257. Let's see, 100 and 257. It's going to be about here. Oops. And I like to label my points. 100, 257. Okay, go ahead and try plot the other points by yourself and check back in with me in a second. Alright, so the next one we have is 102, so about here somewhere. 102 and 264. About there. 102, 264. So we've done that one, that one. Next one, 103, 274. 103, 274, about here. Yeah, we're going to run into the chart. Okay, so 101 and 266. 101 here. 266 a little higher than the 265. Then 105, 277. 105, 277. Oops, it looks like it's inside our chart here. So for labeling it, I'll draw an arrow. Next, we have 100 and 263. 100, 263. Right about there. Next, we have 99 and 258. 99, 258, about there. And then a 105, 275. Right below. This one right here. 105, 275. Once again, this is just a rough sketch. Okay, so we drew a scatter diagram. So one thing to note about scatter diagrams, you do not connect the dots. You leave them as they are, so don't try to draw out some sort of connection. Now let's take a look. As I said, do not connect the points when drawing a scatter diagram. So scatter diagrams show the type of relationship that exists between variables. Our goal in interpreting scatter diagrams is to distinguish scatter diagrams that imply a linear relation, a nonlinear relation. Ooh, it didn't leave much room there. Or no relation. So here are the different types of relations, or we're going to determine the kind of relations in the following scatter plots. So notice our first one right here on the left. And normally when you read left to right, as we do when you read a book or any other sort of document. You always start on the left side and you read to the right. Just like how I read the instructions here. Determine the kind of relation. We read from left to right. Same as how you do with graphs. So going from left to right, what do we notice about our dots? If we follow them, they start going upwards. So this would be called normally a positive relation, but we would call this one a linear relation because it has an upward and also sort of a line-like motion. Now the next one. Same idea. Reading from left to right, our relation seems to be going in a nice straight pattern, which would make it linear. If we look at the next one, reading from left to right, it looks like it starts off linear, but then it turns back down. So it no longer follows a straight path, because remember, lines are straight. So this is nonlinear. And let's take a look at the next one. Reading once again, left to right. Starts out linear, but then it goes back down. And then it goes up again. But still it's not creating one continuous straight path. So this is once again nonlinear. And now for this one, reading from left to right. There really does not seem to be a relationship of where the data is heading together. It just seems to be sort of scattered around. So this one would actually be no relation. Just a small visual there. So by definition, two variables that are linearly related are positively associated when above average values of one variable are associated with above average values of the other variable. and below average values of one variable are associated with the below average values of the other variable. That is, two variables are positively associated if, whenever the value of one variable increases, the value of the other variable also increases. Two variables that are linearly, that's a hard word, man, related are negatively associated when above average values of one variable are associated with below average values of the other variable. That is, two variables are negatively associated if, whenever the value of one variable increases, the value of the other variable decreases. Okay, so for positive, everything is increasing. For negative, one increases, the other value decreases. In other words, if two variables are positively associated, then as one goes up, the other also tends to go up. If two variables are negatively associated, then as one goes up, the other tends to go down. So, Objective 2. Describe the properties of the linear correlation coefficient. So it is dangerous to only use a scatter diagram to determine if two variables are linearly related, as it can often depend on how you scaled your graph. For example, let's go back to what I did up here. Notice, from here to here, I covered 98 values. But in the exact same looking space, I only covered one value. One value, 1 unit, 1 unit. My scaling was really off. So, depending on the way I scale my graph, I could trick your eye into thinking there is some sort of correlation. So to make sure you don't end up tricking someone into thinking there is a correlation when there isn't, we have a mathematical way to check for a correlation. So by definition, the linear correlation coefficient, or Pearson product moment correlation coefficient, is a measure of the strength and direction of the linear relation between two quantitative variables. The Greek letter rho, kind of looks like a P, represents the population correlation coefficient, and R represents the sample correlation coefficient. Once again, we're looking at population versus sample. And we present only the formula for the sample correlation coefficient. So the sample, we have R equals the sum of x sub I minus x bar all over S sub x times y sub I minus y over sy all over n minus 1. So what do each of these values stand for? Well, this is where x sub I is the ith observation of the explanatory variable. We've seen that before. X bar is the sample mean. S sub x is the sample standard deviation of the explanatory variable. So this is new. Y sub I is the ith observation of the response variable. Then y bar is the sample mean of the response variable. And S sub y is the sample standard deviation. And n is the number of individuals in the sample. So we have some new concepts here. Not only do we just have the mean and sample standard deviation, but we have it for each of the variables. They have their own mean, observations, and standard deviation. So let's take a look at the properties of the linear correlation coefficient. So the properties can be found on page 176 of your textbook. So number 1, the linear correlation coefficient, which I will just call LCC, is always between -1, oh, let me just rechange this. So it's always between -1 and 1, inclusive, which means we can include them. Okay? Or another way of putting it, when we use the variable r, right there, r for a linear correlation coefficient. Second, if r equals 1, plus or positive 1, then a perfect positive linear relation exists. between the two variables. If r equals -1, then a perfect negative linear relation exists. And 4. The closer r is to +1, the stronger the evidence is of a positive association. Oops, the loser. The closer r is to +1, the stronger the evidence of a positive association between the two variables. And 5. Pretty similar, except with negative. So the closer r is to -1, the stronger the evidence of, and this time, a negative association between the two variables. And 6. If r is close to 0, then little or no evidence exists. Of a linear, and note here we say linear, relation between the two variables. So note, we're saying there's no linear relation. We're not saying that there does not exist a relation, because there are other types of relations. And 7. The linear correlation coefficient is a unitless measure of association. So LCC is unitless, as in no dollars, no miles, no ounces. You don't have a unit. So the unit measure for x and y does not apply to r. Let me change that to 2. And lastly, the correlation coefficient is not resistant. So the correlation coefficient is not resistant. That means it can be swayed by either large pieces of data or some other odd observations. So therefore, an observation that does not follow the overall pattern could affect the data. For more examples of what different types of relationships look like, you can look on page 176 to get an idea of some of the different values for r and what kind of relation it might graph. Okay, so now let's take a look. Oh, one thing to note. A linear correlation coefficient close to 0 does not imply there's no relation, just no linear relation, as I highlighted previously. So our third objective, compute and interpret the linear correlation coefficient. So in practice, linear correlation coefficients are found using technology, which you can use on your homeworks as mentioned. Just for the exam, I will be having you do things by hand, which means you'll have smaller data sets. However, we will work out one problem by hand. Also, exam problems should all be done by hand, as I mentioned. And you may use technology for homework problems. Once again, if you ever need help with technology for homework problems, just send me an email and I'll be glad to help you figure that out. Example 4. For the data provided, compute the linear correlation coefficient. A scatter diagram of the data is provided below. The dashed lines on the scatter diagram represent the mean of x and the mean of y. Okay, so we're given our data and our scatter diagram. Now, how do we go ahead and compute this? Well, step one, we're going to compute x bar, standard deviation of x, y bar, and standard deviation of y. Okay, so we are going to be given that s sub x is 2.44949, and s sub y is 5.612486. Okay, so just writing that down, we have s of x is 2.44949. X bar, how do we find that? Well, it is actually given right here, equal to 4. S sub y, standard deviation of y, given right here is 5.612486. And lastly, the mean of y, which is going to be 10. Now, next step. We're going to go ahead and set up a chart like we do for other examples. So we have our x and our y values. And then we're going to compute x sub I minus x bar all over s of x y sub I minus y bar all over s sub y. And then, lastly, we'll compute the multiplication between those values. And we'll plug this into the formula in the end to find our answer. Let me go ahead and shorten this a little bit. Okay, so let's see. For x, we're given 1, 3, 3, 6, 7. 18, we're given 18, 13, 9, 6, and 4. And remember, that is what we're given above here. Oops, right there. So let's go ahead and compute these values. So for this one, we're going to do x sub I minus x bar over s of x. I'll just go ahead and write that out on the side so you get an idea of what I'm doing. I'm doing 1 minus the sample mean of x, which was given as 4, and dividing that by the standard deviation, which is 2.44949. And I'll do that for each of the values here. So go ahead, pause the video, try out those values by yourself. Okay, so working that out, you should get each of these values for the above. And then next, go ahead and work these out and check back in with me in a second. So, I'll do the first one with you though. It's going to be 1, so my 18, my y value, minus my y bar, which is 10, divided by my standard deviation of y, which is 5.612486. And calculate that out each time using the different values given for your y. Alright, so those are the values calculated out for y. And next, for the next step, you're going to go ahead and do the multiplication between each of those values. Let me just real quick erase this and give me a bit more space to write out what we're doing. So for the first column, it would be negative 1.2247 times the 1.4254, which is this value times this value. And then do the same for each of the next following columns. Once again, I'll pause the video and have you check back in with me in a second. Alright, and how we have the values figured out over here on the side. So we can use that to calculate the sum of x sub I minus x bar, the mean, times this, or divided by the standard deviation of s, y sub I minus y bar, so y mean, divided by s sub y. Calculating that out, so adding all these values up for the sum, we'll end up with negative 3.7 8 to 4. Okay, so now we're almost done. The last thing, let me go ahead and box off our chart here. The last thing we're going to do is calculate the linear correlation coefficient. So that's going to be, remember, as the formula was written out. Let me just go ahead and write that down real quick. Divided by, and minus 1 are observations. That's going to be the negative 3.7824 divided by, and how many observations did we have? Well, we had 5 observations because we have 5 data points. So 5, 1, 2, 3, 4, 5. 5, oops. 5 minus 1. And simplifying that out over here, we get R equals, plugging that into the calculator, negative 0.946. Our linear correlation coefficient done by hand. Once again, for the homeworks, feel free to use StatCrunch if the data numbers are very large or the data sets are large, but if the data amounts are small, make sure you know how to do them by hand. Now let's take a look at Objective 4. Determine whether a linear relation exists between two variables. So what you might be asking yourself is, how do I know if the correlation between two variables is strong enough for me to conclude that a linear correlation exists between them? Well, we have the steps for testing a linear relation. So step 1. Determine the absolute value of the correlation coefficient. Second, we're going to find the critical value in the table from Appendix A. Okay, so in the back of your book, there are a bunch of tables, and they all have different names. We're looking for Table 2. So find the critical value for the given sample size. And I'll upload a video for this specific piece of using the table in your video help section of the resources in Laulima, so make sure to look for that. And step 3, if the absolute value of the correlation coefficient is greater than the critical value, a linear relation exists. So, if the absolute, I'm going to abbreviate here, absolute value of the correlation coefficient is greater than the critical value a linear relation exists between the two variables. Otherwise, no linear relation exists. So if it's smaller, no linear relation exists. Now let's take a look at Figure 8, which is on page 179, for visual on testing the linear relation. So if we had a number line, here's 0, here's negative 1, and here's 1. And let's say you have a negative critical value that you found, or maybe you found a positive critical value. Remember, we're looking at the absolute value. Absolute value is just talking about the distance from 0. Okay, so that's what absolute value is. So if you're close to negative 1, you have a negative association. But if you're closer to 0, then there is no linear association. Same for on the positive side. If you're closer to 0, there is no linear association. But if you're close to positive 1, then you have a positive association. So the closer you are to 1, the stronger your association, that's positive. The closer you are to negative 1, the stronger your association is, that is negative. Now let's take a look at example 6. So we're going to use the results from example 3 to determine whether a linear relation exists between the club head speed and distance. So what was our results? Our results were r equals negative 0.946. So let me go ahead and write that down. So our correlation coefficient was r equals, oh, and I totally forgot what it was, 0.946. Actually, it was a negative 0.946, and let me change that 0. It looks like a 6. All right. So remember, the first thing we're going to do is take the absolute value. So the absolute value of negative 0.946 is going to equal 0.946. Next, step 2, find n. So our sample size was 5, and check table 2. And check table 2 in Appendix A, which I mentioned I will make a video on this. So table 2 in Appendix A, I'll just go ahead and write down what it says. For table 2, for your n value of 5, it says that our critical value is 0.878. So this is mentioned in the table, which once again, I'll make a video on how to look at that. So in the table, my critical value is 0.878. And what were we told to look at? We want to see if it's greater than this. So step 3. Because the absolute value of negative 0.946 is equal to 0.946, which is greater than 0.878, my critical value. So since it's larger than our critical value, what do we know? Well, since our value used to be negative, this means we have a negative relation. Association. Okay, now let's take a look at the next part. And there are some typos in here. Sorry, I hopefully have fixed it by the time you get your notes. So for objective 5, if data used in a study are observational, we cannot conclude the two correlated variables have a causal relationship. For example, the correlation between teenage birth rate and homicide rates since 1993 is 0.998. But we cannot conclude that higher teenage birth rates cause a higher homicide rate, because the data are just observational. In fact, time series data are often correlated because both variables happen to move in the same or opposite direction over time. Both teenage birth rates and homicide rates have been declining since 1993, so they have a high positive correlation. We have a question. Is there another way two variables can be correlated without there being a causal relation? And the answer is yes. Through something called a lurking variable. So like the word lurking, it's hiding somewhere, not quite easily to be seen. By definition, a lurking variable is related to both the explanatory variable and the response variable. Let's take a look at example 8. Because colas tend to replace healthier beverages, and colas contain caffeine and phosphoric acid, researchers Catherine L. Tucker and associates wanted to know whether cola consumption is associated with lower bone mineral density in women. The scatter plot provided shows the typical number of cans of cola consumed in a week, and the femoral neck bone mineral density for a sample of 15 women. The data were collected through a prospective cohort study. The data was plotted on the scatter diagram below, and the correlation number of colas per week and bone density is given. Nice, we don't have to find it. The critical value for the correlation with n equals 15 from table 2 is also given, so we don't even have to look at the table. Question A, what kind of correlation exists? Well, to find this out, I need R. And they already give me R, my correlation. They give it to me, negative 0.806. So how do I find out what kind of a relation? Well, I take the absolute value. And that is 0.806. Then what do I want to do? I'm going to compare it to my critical value for my sample size. So my sample size was 15 because we had 15 women. And the critical value given from the table is 0.514. So ask ourselves, is 0.806 larger than 0.514? The answer is yes, it is greater. Awesome. So since it is greater, let's take a look at our sign. We had a negative. That means a negative correlation exists. So we conclude a negative linear correlation or relation exists. So part B. Can the authors conclude that an increase in the number of colas consumed causes a decrease in bone mineral bone mineral density? Identify some lurking variables in the study. Alright, so can we conclude? Well, since the data was just observational, we cannot claim that increased cola consumption causes a decrease in bone mineral density. So we cannot claim it. We cannot claim that increased cola causes a decrease in bone mineral density because this data was observational. So what lurking variables could there be? Well, for example, maybe the age of the people. Or maybe their BMI, body mass index. Or height. Maybe smoking. Maybe lots of other things. Physical activity, when they got measured, menopause status, and all of the sorts of things. There are lots of different things that could be there because this was just observational. It wasn't a carefully planned study through a designed experiment. So remember, to claim causality, to claim causality, we must collect data through a designed experiment. Okay, remember that. So because we didn't have a designed experiment, we cannot claim causality. Because there are all sorts of lurking variables that we didn't take into account when just observing these people. So this is an actual study, I believe, and the authors were careful to say that increased cola consumption is associated with lower bone mineral density. So we can say it was associated. We can say it is associated. But we cannot claim causality because it was not a designed experiment. Alright, once again, you can use StatCrunch or Excel to do your homework problems, but make sure you know how to do these problems by hand. Alright, that's it. If you have any questions, please email me.